All right, so we're going to be doing 6.6 here, which is properties of kites and trapezoids. This warm-up kind of covers 6.4, properties of special parallelograms, so we're going to go ahead and go over that right now. So feel free to pause this and kind of think about it on your own first, and shoot, even do the maze if you want to, but I'm going to be focusing on this. The diagonals of a square are perpendicular. So let's think about this. So we have a square, the diagonals are perpendicular. That is a property that we probably should be familiar with. This is a property of rhombuses, that the diagonals are perpendicular. But remember, a square is a rhombus, right? All the sides are equal. So this one is true. The opposite sides of a parallelogram are congruent. That's also true. That is one of our properties of parallelograms. The opposite sides are congruent, right? That say this side here and these two sides. So this one's also true. Third one, the diagonals of a rhombus are congruent. That one is setting off some alarm bells. I am thinking that might not be correct. So let me sketch out a little rhombus here. So here is something of a rhombus. I guess I didn't do a great job with that, but that's okay. Rhombus. When I have a rhombus, I think that usually I have a diagonal that's longer than the other. So usually there's one of these two diagonals. I'm thinking, let me mark this one blue instead. I'm thinking this diagonal actually looks to be longer. And yeah, that's definitely the case, right? So this is a property of rectangles, that the diagonals are congruent. And a rhombus is not a rectangle. These, at least it doesn't have to be. It could be, but usually it is not. So this one is one that is not true. It is not always true that the diagonals of a rhombus are congruent. Last property here is consecutive. Consecutive angles are supplementary. That is true, right? That's a parallelogram property. These two angles would be supplementary. And a rhombus is a parallelogram. So this one would also be true. All right, let's go ahead and jump into 6.6, kites and trapezoids, with a little Admiral Akbar. All right, here is our family tree of quadrilaterals. So over the last couple lessons, we were talking specifically about parallelograms, all the different special parallelograms. We're going to delve into these other types of quadrilaterals that have lots of special properties associated with them as well. So the trapezoid and the kite and the isosceles trapezoid. They don't fit in this category, at least by most definitions. We don't tend to. There are some questionable links in here. Some definitions of trapezoids can actually kind of let them kind of fall under the, or I guess some definitions of trapezoids allow parallelograms to actually be a type of trapezoid, because we have parallel sides here. But for a, if you define a trapezoid to say it has one pair of parallel sides, well, that's true for parallelogram, it's true. So parallelogram is just a special trapezoid, right? So if you're not precise with your definitions, there can be some more overlap here, and some people do include them in these ways. Same thing with a kite. Some people say that a kite, a rhombus is actually a kite, because when we look at a kite, it means that the consecutive sides, the sides that are next to each other, are congruent. And well, just for a rhombus, all the sides are congruent. So the ones that are next to each other are congruent for sure. So some ways that we define these different things, if you're not careful or exclusive in your definition, there is a little more overlap. We're going to keep it pretty clear so that these don't fit in this way, that they kind of fit in their own silos, so to speak, but some people do define them in different ways. All right, so let's go ahead and talk about a kite. So a kite is a quadrilateral with exactly two pairs of congruent consecutive sides. So this word exactly really sort of helps, exactly two pairs, helps exclude rhombuses from what we were talking about before. But let's go ahead here. So one pair is here, AB and AD. That's one pair of consecutive next to each other, congruent sides. And BC and DC are the other pair. That makes it a kite. Here's a nice picture of a kite too. Okay. kite theorem. So one theorem of kites is that the diagonals are perpendicular. Diagonals are perpendicular. That's a property of rhombuses, right? Why can't a kite be why can't a rhombus be a kite? You know, so this is where there's one of these things of the specificity of your definition, the way that you sort of write it to exclude certain things. They still might have common properties. So this is also a kite, the kite property and a rhombus property, which we're kind of seeing that overlap between these shapes. Anyway, perpendicular is great. It makes us have a bunch of right angles here in the middle, and these are all now right triangles. So right triangles are great. We can use Pythagorean theorem, we can use trig, we can use all kinds of things. All right, so here's a practice problem using that property. Again, we are looking for the perimeter, so the outside shapes, and this is a kite. So these sides here are congruent, and these sides here are congruent. And all of these angles in the middle are right angles, so all 4 of these colored triangles are actually right triangles. So I can find the lengths of the perimeter by using the Pythagorean theorem. If I look at this, say this orange triangle, for instance, and I look at sort of what's marked on there, and I need to find the length of QR, right? QR, that's one of the sides I need to actually get my perimeter. I see this side over here is 13, this is a right angle, and this side is 16. Just missing the hypotenuse. I can use Pythagorean theorem. So let's do that. 13 squared plus 16 squared equals c squared. I'm going to use my calculator to make this go a little faster. So that's 425 equals c squared. And then I'll take the square root of that. Now we could write this in 2 different ways. We could either keep this exact like this, or we could get a decimal version and call this around 20.6. To make this problem a little easier, I'm going to go with the decimal version. So this one is 20.6 and 20.6. Great. Now we just need to do the same thing with one of these triangles at the bottom of our figure, either the green one or the blue one. So I'll do the blue one here. And so we want to find the length of PS. And we know this is 22 and 16. So again, we're missing the hypotenuse. Pretty easy. 16 squared plus 22 squared equals c squared. Using my calculator here, I get 740. And then square root that. I get 2 square root 185. Or as a decimal, again, to make this a little easier, we're going to call that 27.2. So that's 27.2 and 27.2. Now, I could use these exact values that we did take the time to calculate and find my perimeter. I have 2 of these and 2 of these, and I could write that out as an expression. So as an exact, you know, if you really enjoy that, it would be 2 of these, so that's 10 root 17, plus 2 of these, which is going to be 4 root 185 inches. That would be our exact perimeter. No rounding, exact simplified radical form. Great, but I don't need to do that. I'm going to go ahead and estimate my perimeter using decimals. I have 20.6 plus 20.6 plus 27.2 plus 27.2. Let me just go ahead and do that. And 95.6. So approximately, that's going to be pretty close, right? I don't know what this exactly ends up being, but I mean, as a decimal, if I get an approximation, I don't know how close this is, but it's pretty close, I bet. So we'll be happy with that answer. Okay. Kite theorem 2. So the opposite angles here, one set of opposite angles are going to be congruent. Not true of these other ones. Not true of these other ones here. Pay careful attention that these angles are in between the non-congruent sides. Same over here. Those are the ones that are going to be congruent. This is pretty easy to demonstrate, again, by drawing a diagonal, like we've done a lot of times, and showing that these 2 triangles on the top and the bottom are congruent by SSS. So ABC, ADC are congruent by SSS. And angle B and D are simply corresponding parts. So angle B would be congruent to angle D by CPCTC. Pretty easy proof. Actually, this one's is easy. I have used the term easy a lot in some cases where it maybe wasn't easy, but this one is. All right. This is great. This helps us find some angles in here. To further compound this, there are some other things that can go on with this same triangle congruence, right? B and D correspond, but it's also true that, say, this angle here and this angle here are equal. So this angle A has been bisected. Same over here. These two angles would also be true. So angle C was also bisected by this diagonal. So this is some more stuff that's at play that's, again, based on this CP-CTC relationship that we're using to prove B and D. I'm going to make use of this. This is why I'm pointing it out right now. All right, so here is a kite with some angle measurements marked, and we have our long diagonal. We can see that this angle up here, this whole thing is 104. So that's also true over here using that property from the last page, that this whole thing over here is 104. These are the angles. They were the B and D from the previous problem. Also, just sort of looking at it, this one being 49, remember, that also means this one is 49. This angle is cut in half. Also, using some of the other properties that we looked at on previous pages, right? These are all right angles. Tons of things we can do here. Let's keep in mind what the problem is actually asking us to do. We're looking for the measure of VWX. VWX. So we are actually looking for this angle right here. We want to know what that angle is. I see two pretty good approaches. We could break it up into these smaller triangles. We know angles in here that we could figure out all the angles in this triangle here. I guess this would be VYX, this triangle, to help find this. We could use that to find this angle and then go that way. I'm going to do that first. So I have 49 and 90 and whatever this is. So 49 plus 90 is 139. 180 minus 139 is 41. Okay, so right here is 41. These two angles together make 104. So if I do 104 minus 41, that's 63. That's this piece, 63 and 41 make 104. And now I have 63 and 90 and the one I'm looking for. So 63 plus 90 is 153. 180 minus 153 means this is 27 degrees. So cool, found the angle, it's 27 degrees. That was a bit long. There's a faster way to go about this. So let me just erase some of the things that I have here just to make this go a little faster. I'm still going to arrive at 27, but I just want to show it a little bit quicker than what I just did. It all hinges on noticing a bigger triangle that can help us even more. So if I highlight this one in yellow, a bigger triangle here can make this go a little bit easier. In this larger triangle, I know this one's 49. I know this one's 104. And I'm missing this. It's more of a straight calculation. So 104 plus 49. I add those together, I get 153. So that's this angle here and this angle here. And I'm missing the third one. So 180 minus 153 is going to give me that to be, again, 27. Same answer either way. That kind of helps confirm both of them, to be honest, that 27 was right. There's even a third way to go about this that involves, instead of triangles, to actually look at our entire quadrilateral. You can see 104. These two together make 98, 104, and we can figure out this whole thing, cut it in half to get 27. I'm not going to go through that one. I don't think that's faster than what we just did, and we're just going to get the same answer. So Next shape, it's a trapezoid. Okay, so a trapezoid is a quadrilateral with exactly one pair of parallel sides. So here and here, that language there, exactly one pair of parallel sides, that helps us exclude parallelograms from the definition because they have two sets, so that excludes parallelograms. Again, not everyone defines them that way, so it's fine if you don't, or if you see somewhere that doesn't make it wrong. It's just the way we're going to do it. Each parallel side is called a base, so we have two bases. And then the non-parallel sides, we call those legs. Legs, that we also use that for right triangles, but these are different. These are legs of a trapezoid. The base angles of a trapezoid are consecutive angles that share a base. So A and D in this case are base angles, and B and C are base angles. They share this base. A lot of vocabulary there. One thing, if the legs of our trapezoid are equal, we actually call this a special name. We call it an isosceles trapezoid. Trapezoids have a lot more properties if they are isosceles. So we're going to spend more time talking about isosceles, but we'll look at trapezoids first. So there's one theorem or one property for trapezoids that we're going to see. Angles that share a leg, so consecutive angles that share a leg, are supplementary. The numbering got thrown off here, but this was 1 and 2, 3 and 4 up there. Why? They are same side interior angles, right? If I kind of draw that out, parallel line, our legs are transversals, so 1 and 2 are same side interior, they're supplementary. 3 and 4 are same side interior, they're supplementary. It's maybe not a theorem, but it is something that applies specifically to trapezoids, to all trapezoids, so it is worthwhile to know about them. Let's find the measure of angle R in this trapezoid. So again, we're making use of that theorem that we just said. These are two angles, they're consecutive, and they share this leg, right? We know this is the leg because it's not parallel. These sides are the parallel sides. So this is a leg and this is a leg. These are consecutive, they're supplementary. So setting up my equation here, combining like terms, I get 14x plus 12 equals 180. Subtract 12 on both sides, I get 162. And then let's do a little division. 162 divided by 14. That is not great there. Okay, 162 over 14. Again, this is a kind of a messy decimal. I suppose this, maybe there was something else that needed to go on with this. This is a fractional. Maybe keeping this in a fraction is a better answer. But instead of finding R, I'm just going to finish by having solved for that. I'm satisfied there. Because x being equal to this messy decimal, I don't love what answers that's going to give me. So I'll stop there. All right, so isosceles trapezoids, we're going to investigate the isosceles trapezoids. They have really lots of properties that are associated with them. So first one, the base angles are congruent. So B and C are base angles, A and D are base angles because they share a base. Maybe we can call this base 1 and base 2. Doesn't matter which one, but B and C share base 1, A and D share base 2. Yeah, so if you know any one angle in an isosceles trapezoid, you should be able to find the rest of them. It's pretty simple, right? If you know A, D is the same, supplementary to B, and B and C are equal. Pretty easy relationships here. Yeah, any single angle should give you the rest of them in an isosceles trapezoid. So let's go ahead and look at this one. We can kind of run through it pretty quick. Base angle. The other base angle is also 49. we're going to be supplementary to the other set of base angles. So if I do 180 minus 49, that's going to give me 131. And the base angles up here are also equal. So once you know one angle, you can kind of make sure you know the rest, and it's pretty easy. As long as it is an isosceles trapezoid, which in this case, right, we can see the legs are equal, it is isosceles. Okay, here's another theorem here. So we can know that a triangle is, a trapezoid is isosceles if we know that we have congruent base angles. We don't even need to know that the sides are equal. If the base angles are congruent, the legs will be equal. We can do this, but I'm not actually going to go through the proof of what that would look like. Just clear this. Another theorem, another property of isosceles trapezoids is that the diagonals are congruent. That's similar to rectangles, right? Pretty easy to show. Again, it's really a matter of showing that we have some overlapping triangles that are congruent. So this triangle is congruent to one that overlaps with it right here. If we can show these two triangles congruent, the AC and BD are corresponding parts. Therefore, there we go. They'd have to be congruent. Okay, let's go ahead and do this practice problem here. So RW is 17.5, 17.7, sorry, I misspoke. RW 17.7, that's RW. SV, this whole thing from S to V is 23.3. Well, pretty easy. We're supposed to find TW. So we know that the diagonals overall are going to be equal. So if we call TW X, we can say 17.7 plus X is equal to 23.3. Subtract this on both sides. So 23.3 minus 17.7 is 5.6. There we go. TW is equal to 5.6. Here we have one that's going to make us have some algebra to it. So we're going to find a value of z that makes this isosceles. Remember, if the base angles are equal, it is isosceles. So we're going to solve it so that they are equal. 12z squared equals 7z squared plus 20. So we'll subtract 7z squared from both sides. Get 5z squared equals 20. Divide by 5. Get z squared equals 4. And then take the square root. So z equals 2. Technically, there's another solution to this, that it equals -2. But that's going to give us the same thing regardless. So it won't change the value of our angles, even though technically this is a solution to that equation. Anytime you take the square root to solve an equation, you get two answers, a principal root, which is positive, and the negative root. So anyway, this makes this 2, which is 12 times 2 squared, or 12 times 4. So this angle is 48. And obviously this one would be the same, 48 degrees, 48 degrees. Okay. I think this is the last one here, so we'll just go ahead and go through it quickly. Again, this one we are trying to find a value of y so that this is isosceles, so that the legs are equal. So it says 7y minus 6 is mq. That's one of our diagonals. mq is a diagonal. And LP is our other diagonal. We know that the diagonals are equal, right? LP is our other diagonal. If the diagonals are equal, that makes it isosceles. So simple equation here, 7y minus 6 is equal to, right? We're really saying the two diagonals are equal. That makes it isosceles. 4y plus 11. That's going to be 3y equals 17. y equals 17 divided by 3. That's, again, not a beautiful answer. We'd get a decimal for this, so I'm going to leave it the way it is, right? We'd get 5.6 repeating if we went ahead and divided that out. Okay. Homework. Here are the textbook problems from the homework. Make sure that you upload number 29 and 30 to the Google Classroom assignment, and I'll see you guys later.